When it comes to current divider laws, in my book, there's two approaches. The first approach, first approach is the one that I assume you all have seen in school, which is you have some current source, you have a resistor, two resistors in parallel. Let's call this R equivalent B, R equivalent A, IS. Let's assume this current is R equivalent B. This current is R equivalent A. So R equivalent A is equal to IS divided by R equivalent A plus R equivalent B times R equivalent B. And R equivalent B is equal to IS divided by R equivalent A plus R equivalent B times R equivalent A. So that one we've been taught. But what about the second approach, or what I'm calling the second approach? What about if we have this circuit? Let's assume this is R equivalent B. Let's assume this is R equivalent A. Let's assume this is R equivalent C. Let's assume this is VS. So in the first approach, what do we have? We have one current source and two networks of resistors that are in parallel, to each other and IS. To each other and IS. But here, in the second approach, we have a voltage source in series with R equivalent C, and then we have two resistors that are in parallel to each other, and as a network, they're in series to R equivalent C. So let's assume the current that we're going to be solving for is R equivalent B, R equivalent A. Let's call this current IX, and that's that there. So when I look at this circuit, let's just think of currents. IX is the current that's splitting. It's splitting into two different currents. IX is the current that's splitting, and it's splitting into two different currents, R equivalent B and R equivalent A. If we look above, IS was the current splitting. So technically, I could still use this and that equation, but instead of IS, I'm going to have IX. So let's write those right off the bat. Right off the bat, IR equivalent is terrible. IR equivalent A is equal to IX over R equivalent A plus R equivalent B times R equivalent A, and IR equivalent B is equal to IX divided by R equivalent A plus R equivalent B times R equivalent A. Okay, so the question that is remaining is, what is IX? Well, IX is the current that is going through R equivalent C, and it splits into IR equivalent A and IR equivalent B, which means let's group R equivalent A and R equivalent B together since they're in parallel. So now this is IX, R equivalent C, R equivalent A, in parallel to R equivalent B. There's VS. And we could even take it one step further. Simplify. And again, we got here through simplify. And we could take it one step further. This is VS. This is R equivalent C plus R equivalent A parallel to R equivalent B. This is IX. Using Ohm's law, we can find out what IX is. VS is equal to IX times the resistance, which is R equivalent C plus R equivalent A parallel to R equivalent B, right? Therefore, IX is equal to VS divided by R equivalent C plus R equivalent A parallel to R equivalent B. And because now we have IX, we could go back to these two equations, which means what? Given this drawing, well, I'm not going to redraw it. It means maybe I should have the drawing down there for those taking notes while watching the video. Copy, text mode, and I'm gonna paste right there. There you go. All right. So what we now have is IR equivalent A is equal to what? In parentheses, VS divided by R equivalent C plus R equivalent A parallel to R equivalent B divided by R equivalent A plus R equivalent B times R equivalent B. This is IR equivalent A. I just plugged in what IX is. This in parentheses right here, that's IX. And then, similarly, IR equivalent B is equal to what? Same thing. VS divided by R equivalent C plus R equivalent A parallel to R equivalent B. B divided by R equivalent A plus R equivalent B times R equivalent A. So this is my second approach. Okay, so this is approach number 2. This was approach number 1. Why do I call them different approaches? Because in this circuit shown here, you have the ideal easy spoon-fed case. I shouldn't use the word easy. Spoon-fed ideal best case scenario with homework and exams, where you have a current source in parallel to 2 resistors, and each resistor can be equivalent to a network of resistors. That's why I put R equivalent A. Okay, but here in the second approach, what do you have? You have one voltage source. You have 0 current sources. And you have an R equivalent C in series with R equivalent A parallel R equivalent B. So one can argue this part looks like approach number 1. But what's different is that we have a voltage source on the left side of that region that I just circled in red. So in homeworks and exams, you'll usually see this kind of circuit, and they want you to know the current. They want you to solve for the current flowing through R equivalent B. So current source, I mean, if you have these 2 equations at hand, you can use either of them and just plug and chug rather than doing, I don't know, mesh analysis per se. Okay, so I'm not going to do a full example, but I'm just going to say like example 1. let's say you have some circuit like this in your life. Right, let's say this is R1, R3, R2, R4, R5, R6. Then you would need to simplify that to this. Because started from the bottom, now my whole team up here. So you can simplify that circuit on the left to the circuit on the right. And then you could solve for the currents flowing through them if you had to in a homework or an exam. Similarly, if you had a problem like this, where this is R1, R2, R3, R4, you could simplify that too. Again, started from the bottom of my whole team here. So you can definitely simplify the circuit on the left to the circuit on the right. Okay? And then you could solve for currents. That's what I'm just trying to show here. That there are two approaches, and I suggest that you have these two formulas in your formula sheet if you need to create a formula sheet or have them at hand in for homeworks. Again, this is just preference. If you don't want to have the second approach in your notes, that's cool, but just letting you know, you're not always going to have this kind of circuit showing on your screen. You're not going to always have this for exams and homeworks. Normally, you're going to have a circuit that looks something like this, or that can be simplified to the circuit shown on your screen right now. So, thank you for joining.